Now let's talk about how to differentiate a quotient. So here's a thought experiment for you. Is the derivative of a quotient equal to the quotient of the derivatives? In other words, does the derivative of f of x over g of x equal f prime of x over g prime of x? Can you differentiate the top and the bottom separately and then find the derivative that way? Well, let's again look at an example. How about x squared plus 1 all divided by x? Well, if this were true, what we're saying here, which we don't know if it is or not, but let's see. Let's say if this were true, then this would be the derivative of the numerator x squared plus 1 over the derivative of the denominator, which is x. And we're just going to put a little question mark above this equal sign here because we don't know if this is true or not. So if we differentiate the top, we will get 2x, and if we differentiate the bottom, we will get 1. So that's just 2x. Well, so is this correct or not? We do have a way to find the derivative of a function like this from before. We can simplify this function by looking at it as x squared plus 1 parentheses times x to the negative 1. And then we can distribute that x to the negative 1 into the parentheses. That will give us x to the first plus x to the negative 1. Now if we differentiate this, the derivative of x is 1, and then we'll add the derivative of x to the negative 1, which will be minus x to the negative 2. This is equal to 1 minus 1 over x squared. Now these things are not the same. We do know that one of these is correct. We do know for sure that this way is absolutely correct here because this is how we've done it in the past, and there's nothing wrong. We've used all of our rules that we have learned so far. So that means that this rule, this way, is incorrect. This means that this statement up here is the derivative of a quotient equal to the quotient of the derivatives is just no, not going to work. I know it's really tempting and it would be really nice if that's how it did work, but it doesn't. It will never work this way. If it doesn't work for one example, then we can't say that it's true for all examples. So nope, never. We have to learn a new rule in order to differentiate a quotient. So here it is. The quotient rule says that the derivative of the quotient of two differentiable functions is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. What a mouthful. Here is what that says in symbols. The derivative d dx of f of x over g of x is equal to the denominator g of x times the derivative of the numerator f prime of x minus the numerator f of x times the derivative of the denominator g prime of x. Then that's all divided by the denominator g of x whole thing squared. Now you'll notice that in the numerator here, this is sort of kind of similar to what we had with the product rule, except there's a minus here instead of a plus that was there in the product rule. With the product rule, the order doesn't really matter because when you add two things together, you can do it in any order. However, with the quotient rule, when you're subtracting here, it really does make a difference that this g of x here comes from the denominator and the first derivative multiplied here comes from the numerator. Then we do the opposite thing in the second half of the subtraction. Then what we divide by is the denominator squared. This notation is a little clunky, so here are some other ways to notate this. Here it is in a sort of informal way. If we think of a fraction as high over low, high being the numerator and low being the denominator, then the derivative of that, so prime here, will be low bottom times derivative of the top, so d high, minus top high times the derivative of the bottom, so times d low. And that's all over the denominator squared, so it'll be low squared. So this one's kind of fun because it's sort of easy to memorize, like low d high minus high d low over low low or low squared. So if this is something that makes sense to you, then feel free to use that. I will actually use this way that I'm about to write to help us organize our work for the quotient rule. I like to use n and d for numerator and denominator. And if we're finding the derivative of that, then it's going to be denominator times numerator prime minus numerator times denominator prime, and then that's all over the bottom or denominator squared. It is important to know what these formulas are. I would focus less on memorizing the product rule and quotient rule formulas and focus more on understanding how the things fit together. So we have to know how to use these, and you will sort of just automatically memorize these rules the more that you use them. But personally, when I'm using the quotient rule, I don't say to myself, the letters here. I actually have this coming up in my mind, or something similar, something along those lines, which I think this is a nice bridge between the words and the symbols. If you'd like to know an algebraic proof of the quotient rule, meaning why it's true and where it comes from, you can find that on Blackboard under the lecture notes for this section. Here are a couple things to note about the quotient rule. The first note is that we now have two differentiation rules that apply to quotients. I know that the constant multiple rule doesn't look like it has anything to do with a fraction or a quotient. However, we could view the constant multiple rule as looking at it as f of x, some stuff with x, divided by a number. Right? Dividing by a number is the same as multiplying by 1 over that number. So in other words, dividing by 2 is the same as multiplying by 1/2. So we can look at dividing by a constant as the same as multiplying by a constant. So this would be 1 over k times f prime of x, or in other words, f prime of x over k. So for example, we could differentiate a function like y equals x squared minus 3 by looking at it as 1/3 x to the second. Then this 1/3 becomes a constant multiple, and then we differentiate the x squared and multiply it by the 1/3. So something like this does not need the quotient rule. We don't have variable stuff in the denominator, it's just a number. So again, if we have variable stuff over a number in the bottom, that doesn't need the quotient rule. However, if we do have variable stuff up top in a fraction and variable stuff down bottom in a fraction, then you should use the quotient rule on something like this, in most cases. So for example, if you had something like x squared over x minus 1, you have variables up top and variables down in the bottom, and so the quotient rule would be appropriate to use on a function like this. So make sure that you know when to use the constant multiple rule and when to use the quotient rule. The second note, which goes just in line with the first note, is that sometimes we can avoid using the quotient rule unnecessarily. The quotient rule is actually our most complicated formula to use when we're finding derivatives. So if you can avoid using the quotient rule, then you probably should. Pause this video and see which of the functions below will absolutely require using the quotient rule to differentiate. In other words, you cannot use algebra to get rid of the quotient on one or more of these. There is actually only one function shown in this list that 100% requires the use of the quotient rule, and that is this last function here. We have variable stuff up top and variable stuff in the bottom, so that indicates to us that the quotient rule might be needed, but it's really similar to the function right above it. However, in the function above this one, we can rewrite this as x minus 2 over x to the 1/2. Then we can bring up that x to the 1/2 and look at it as x minus 2 times x to the negative 1/2. Then we can distribute the x to the negative 1/2 and write this as x to the 1/2 minus 2x to the negative 1/2. Then we can use our simple derivative rules in order to differentiate this. You can do this process on every single one of the other functions here. For example, the first function can be written as 3x to the negative 2. Differentiating that, you can use simple rules. The second function below that can be looked at as 5 over 8 times x to the fourth. We would differentiate that using the constant multiple rule and our simple power rule. In the second column, we can look at this as 1 over 6 parentheses x squared plus 3x. Here we have a constant multiple times variable stuff. We don't need to use the quotient rule on this. In the example below that, we can look at this as this 5 being a really 1 over 5, and rewriting this as 1 over 5 times 9x plus x to the third over x squared. And then that x to the second in the denominator there can actually come up, and we can multiply by x to the negative 2. Then we can distribute that x to the negative 2 into the other part with the variables here, because we actually now have a product. We don't need the product rule on this, though. This would give us 9x to the negative 1 plus x to the first. Then we have a constant multiple times x to powers added and subtracted together. And it wouldn't be wrong to use the quotient rule on any of these. It's just not very efficient. And brain power is limited these days, so we want to be efficient in how we use ours. As a general rule of thumb, if we are dividing in the bottom by what's called a monomial, meaning a single term, then you can often rewrite your function without a fraction. In this last example here that does require the quotient rule, we are dividing by a binomial, something that has two terms. And if we bring this whole thing up and make it to the negative 1 exponent, we can't distribute into the negative 1 exponent, which is why we can't get rid of a quotient here.